Okay, in this section, we're going to look over the contents from section 1.4, which is experimental design and ethics. So the goal of every statistical study is to collect data and then use it to make a decision. So we have talked a lot so far about identifying the variables, the population, samples, how to collect the sample. So now in this section, we're going to move forward and talk about different designs of studies and experiments. And so typically studies can be broken down into two options. So I'm going to put that here. You can break it down into an observational study or an experiment. When we're talking about an experiment, the purpose of an experiment is to investigate the relationship between two quantities, and we will be applying some kind of treatment. So when we perform an experiment and we apply this a treatment, that group that we apply the treatment to is called the treatment group. And then once we apply the treatment, then the responses are observed and recorded. And then the other part of the population that we do not apply the treatment to is called the control group. And that is where no treatment is applied, and that will allow the researcher to compare the results. And then the subjects in these groups are called experimental units. So they're going to be people or animals or some kind of object. Now, for an observational study, this is the kind of study in which individuals are observed and outcomes are recorded. But this is without applying any kind of a treatment. There is no intervention at all. You literally sit back and observe and collect the information. Sometimes an observational study is better than an experiment because you don't want to apply a treatment if it's unethical. And the example that I would use is when you're trying to collect data on the number of fatalities of people that are in car accidents if they were wearing their seatbelt versus not wearing their seatbelt. And you don't want to apply a treatment in this case and perform an experiment where you put people in cars and crash them into trees and telephone poles, some with their seatbelt, some without their seatbelt, and see what happens. That's completely unethical. So in this case, you might just want to use an observational study where as accidents happen, because they do, you just collect the data. So no treatment is applied for that. Whereas in an experiment, a treatment is applied so that you can record the differences between groups with the treatment and without the treatment. All right, so now when you are studying these quantities to see how they change, typically you have one variable that causes change in the other variable. Okay, and the variable that causes change is known as the explanatory variable. I have all of our vocabulary words listed here as I go through and explain what they mean. So the variable that causes the changes is called the explanatory variable. And in other books, you might see it described as the independent variable or as the X variable. And then the variable that is affected is called the response variable, which is your dependent or your Y variable. So that's your response variable here. Now, sometimes additional variables pop up that cause confusion in a study on what is causing the changes in the variable. And these variables are called lurking variables. And sometimes, and I'll put this in parentheses here, sometimes these are also called confounding variables. And so these variables that you did not take into consideration that pop up during an experiment could cause your results to be inaccurate. So you want to try to take into consideration when you are building or designing your study that you try to eliminate all possible variables except what you're trying to compare. So an example of a lurking or confounding variable, and I found this actually in a book, and I thought it was kind of a cute example that gives a really good explanation of a lurking variable. If you have a researcher and they're doing research and they find that ice cream sales increase when shark attacks increase. Now, that doesn't mean that ice cream sales is causing more shark attacks. That doesn't make any sense. So, but why would one go up and the other one go up consistently? So that's the question, and this is where the lurking variable comes in. It's not necessarily that the ice cream sales is affecting the number of shark attacks, it's the weather. The lurking variable here is the weather, because when it's warmer outside, you have more people going to the beach and buying ice cream, which means by default, if you have more people at the beach and getting ice cream, there's going to be likely an increased number of shark sightings and shark attacks. So in this case, you have that extra variable that wasn't taken into consideration when you're looking at the difference or how those quantities are related. So keep that in mind when you're developing your design of your experiment. Think about other things that might affect your experiment and find ways to eliminate that. So the only variables that you have in your experiment are the two quantities that you're trying to compare. That way there's no confusion and you don't have inaccurate results. Now, sometimes a group in an experiment is given a placebo, which is basically a fake treatment that will not influence the experiment at all. And when you have people that are participating in a study and you are giving them some kind of treatment in one group, the other group, the control group, can see that they're not the ones getting the treatment, and that might influence the results if they know who's getting the treatment and who's not. So that leads us into the idea of what's called blinding. An experiment where you have blinding, that keeps the participants from knowing whether or not they have the placebo or the actual treatment. So a placebo is given to one group, which is the control group, but they're given a placebo because it's not going to affect the results. And then you have the treatment group that's given the actual treatment, and therefore the participants don't know who actually has the real treatment, and that might increase the chances of getting better results. So then you have what's called a double-blind experiment. And this is when both the participants and the researchers do not know who is receiving the treatment and who is receiving the placebo. This is even better to make sure that you have the best accurate results, because that means that the researchers won't be influenced in any way. Okay, so we talked about all of these terms. Let's go down. I'm going to add one more row down here because we have to talk about what's called ethics. Because there is a wide misuse of data and research for advertising and, for example, big pharmaceutical companies and other reasons for financial gain, statistics has developed a bad reputation. And so researchers have a responsibility to make sure that they're using correct methods and that they're not reporting the information incorrectly. So there have been guidelines and laws put in place to ensure that this happens, especially when people are involved in studies. And so some of the basic guidelines are, there's 3 of them that we'll talk about here. And this is specifically for when people are involved in studies. You want to make sure that the risks to the people involved are minimized. Okay, you also want to make sure that participants give informed consent. And this means that the risks of the participant must be clearly explained in writing so that the researchers are required to keep that documentation. And that way, if the participants see that there's a risk that's bigger than what they're willing to take, they can back out of the study. So we want to make sure that there's informed consent and that the researchers document this. Okay, and the last one that we're going to talk about is that data collected from people must be carefully protected for their privacy. Let me write that down too. Okay, so that's the basic idea of ethics. There's more to it than that, but that's just the overall summary. So let's walk through a couple of examples to practice this new terminology. Some of this overlaps, which is good practice. Okay, example 1 says, researchers want to investigate whether taking aspirin regularly reduces the risk of heart attack. There are 400 men between the ages of 50 and 84 that are recruited as participants. The men are divided randomly into 2 groups. One group will take the aspirin and the other group will take a placebo. Each man takes 1 pill each day for 3 years, but nobody knows whether they are taking the aspirin or the placebo. And at the end of the study, researchers count the number of men in each group who have had heart attacks. Okay, so we're going to identify the following values for this study. So the population, remember, when we identify the population, we're looking to see where the focus is on the study. What are the individuals that we're trying to gather information from? And in this case, specifically, we're looking at men between the ages of 50 and 84. So I'm going to put that down for the population. Now we have to be careful when we specify the population that we're giving specific information, because that would misrepresent our experiment. So if I just put down the population is all men, that's not true because we're focused on men between 50 and 84. If I put down people between 50 and 84, that's not correct either because we're specifically looking at men between 50 and 84. So just by missing one descriptive word, it can throw off the focus of the study and the results. And make sure you underline keywords and identify all the important information. Okay, for the sample, that's from the population, the people that we collect the data from. So in this case, it's those 400 men that we're collecting the data from. So I'm going to put down for the sample, it's going to be the 400 men aged between 50 and 84 that participated. Okay, now the experimental units are the ones that participated in the experiment. So these are the individual men in the sample. So the 2 variables that we're trying to compare in this experiment is the medication or the aspirin versus the number of heart attacks. So the explanatory variable is supposed to represent the variable that actually causes some effect in the other variable, the second variable. And since we are looking to see if aspirin affects the number of heart attacks, then the explanatory variable is going to be the aspirin, because that's what we're looking to see if it has an effect on the other variable, which is the number of heart attacks. So I'm going to put down here, it's the aspirin. And then the response variable is going to be the number of heart attacks. or actually, if I go back and read this a little bit more carefully, we're looking to see not the number of heart attacks, but if they've had a heart attack or not. So again, that was me making a mistake. It's very easy to do. It's always important to go back and look at the wording in your question. So the response variable is not going to be the number of heart attacks. It's actually going to be if the individual had a heart attack. So the response variable is going to be yes or no, or positive or negative. So the treatments are the aspirin and the placebo. Oh, although the placebo is, I guess, what you call a dummy treatment, where it should not cause any effects. Oh, there's my ethics. That was supposed to go up top. I thought I missed my vocabulary word, but it got bumped down. You can cross that off. Okay, let's go to example 2. The Smell and Taste Treatment and Research Foundation conducted a study to investigate whether smell can affect learning. Subjects completed mazes multiple times wearing masks, and they completed the pencil and paper mazes 3 times wearing floral scented masks, and 3 times with unscented masks. Participants were assigned at random to wear the floral mask during the first 3 trials or during the last 3 trials. For each trial, researchers recorded the time it took to complete the maze and the subject's impression of the mask scent, positive, negative, or neutral. So we need to identify the explanatory variable. Remember, the explanatory variable is the variable that we are trying to determine if it's affecting the second variable. Okay, so our 2 variables that we're trying to study in this question is the scent of the mask and then the time it takes to complete the maze. So between the 2, the one that we are expecting or are curious to see if it's going to affect the other is the scent. So the explanatory variable is going to be the scent, while the response variable is going to be the time it takes to complete the maze. Now, the treatments that were applied was the masks. You had one that was unscented and one floral scented mask. So let's see, are there any lurking variables? So I would say, in this case, I can't think of any additional variables that might cause incorrect results. That doesn't mean there aren't any, but I can't see any off the top of my head. And that's because everything was randomized and all the people used both treatments. So I'm going to say no here. But I'm also going to add in, you can always discover one after you start your experiment. Right? You don't know what you don't know. But off the top of my head, I don't see any in this question. Okay, so part D says, could blinding be used in this experiment? I don't think blinding will work here because the person that is wearing the mask can clearly tell whether or not they're wearing an unscented or a scented mask. So I don't think you're going to be able to hide that information. So I don't think that would be possible in this case. So I'll write it down as no. Participants can identify if they are wearing a scented mask. Okay, example 3. So the researcher wants to study the effects of birth order on personality. Explain why this study could not be conducted as a randomized experiment. What is the main problem in a study that cannot be designed as a randomized experiment? You can't randomize birth order. You're going to be born if you're going to be born. So that's one issue. You can't say, Sally's going to be born first and then Johnny, and then do it again and say, well, Johnny's going to be born first this time, and switch the order. That's impossible. You can't do that. And then also, when you randomize, that helps eliminate issues. I should put errors, and then I'll put such as finding a lurking variable or bias. So that is all of the big information for Chapter 1. This section concludes Chapter 1. And so looking back and just summarizing what we talked about so far, we have learned that there are many ways to collect data. We learned that categorizing data and understanding the type of data that we have helps us determine the procedures, methods, and the graphical representations that we can use when we're trying to organize our data. And then we also learned, this was a big one, that researchers must work with sample data in order to analyze populations most of the time. Usually your populations are big enough where it's impossible to get data on each individual in the population. That's very rare. So typically researchers will work with samples to draw conclusions. So in the next chapter, we're going to really focus on the shape of the data, more graphs that we can use, and different characteristics of the samples that will help us later draw conclusions about the sample.